We're back to talking about limits of functions again, and we've already talked about this, but let's kind of revisit it, and we're going to have a couple new ideas. One of which I think you'll really like. Um, but the big idea, if we just kind of remember what limits were, is the idea that you've got some sort of function, and then you got some point here, and we'll call that point A, and then you've got a height L, and we're looking at the limit as x approaches a of f of x is equal to capital L. And so if you remember this idea, what that meant was we took some sort of epsilon window around L, so we added an epsilon on the top and the bottom of L to look something like this. And then once we had the epsilon window around L, we asked what does A need to be? And then we made a window like this that we called delta. And so we said, if we pick any point within this delta window, then we get a point within the epsilon window. And so we'll remember this definition. The definition is for all epsilon greater than 0, there exists a delta greater than 0, such that if x minus a is less than delta, then f of x minus L is less than epsilon. And there's one other piece that I needed to add, and it's that we don't want to let A be the point, because we want to be able to deal with situations where we have an empty hole here at that point. And that's something that we like to do. And the reason why we want to define it that way is because in just a little bit we're going to be talking about derivatives, and derivatives are points where that value doesn't exist. Oh, and by the way, I mean, if the value exists, then the problem's not quite as interesting as if it doesn't exist. But if you remember, there's all sorts of interesting consequences. There were all sorts of theorems that connected from that, like the limit, the limit as x approaches a of f plus g of x is the limit as x approaches a of f of x plus the limit as x approaches a of g of x. And this also works if that's multiplication. Here it also works if it's division, although the division requires the g not to be equal to 0. Not to be approaching 0. And then we have kind of these other theorems like our squeeze theorem, the comparison theorem, which we didn't talk about, but I think you all might be able to figure out what that is. We'll revisit some of these things as well. But the first thing I want to go to is the real new idea for today, and that's what's called the sequential characterization of limits. And so the big idea here is that a limit equals L if and only if every sequence, if A of n approaches A, then f of a of n approaches L. So let's grab this picture again that we had just a second ago and see if we can make sense of what this is talking about. So we've got our A, and then I'll draw my picture. I'll draw my picture. Maybe it looks something like that this time. And there's my A, and here's my L. And I've got my windows. So here's my epsilon window around L, and this would be my delta window around A. Okay, and so the important thing is that we have the sequence, A of n sequence, and so if A of n is some sequence made up of points that are approaching A, so for example, A of n could be a bunch of values here that are getting really close to A. Well, what I'm interested in is f of A of n, and that is what happens to those values when I put them on my graph. Right? What's happening to those values? And importantly, those values, if I look at them over here in comparison to L, those values are getting really, really close to that point. So those values are going within the epsilon window of L, just like the function is. And so you can see that this direction of the if and only if seems completely obvious. If the limit exists, if we take any sequence on top of that limit, then that sequence should have the same limit. And that proof will be pretty simple. The second one, which is more complicated, says, well, what if we didn't know what the function looked like? And what if we were in some situation that looked like this, where all we had was a function that we didn't even know what it was, but we knew that every sequence that we drew on there always went to that same point. So if I drew that sequence and that sequence, and then what if I took some points in between there, and then took some points? So every sequence that I can take always ends up going to that same point. Does that mean the function goes to the point? Well, you'll notice each sequence misses some values, right? So there are some missed values, an empty hole there, there's some missed values. And so the question is it still valid if every sequence converges? And the answer is yes, but that's a harder thing to prove. So let's do the first proof first, because that'll be the easiest. So we will assume that that limit is true, and then we will let an be a sequence that's converging to a with none of the an's equal to a itself, because that would kind of mess up that one part of the definition. Well, because this exists, we know, and we're going to let epsilon be greater than 0. And then because we're dealing with this limit, we know that there exists a delta greater than 0, such that if x minus a is less than delta, then f of x minus L is less than epsilon. But now all I have to do is I go, well, now all I have to do is I have to make sure that my an's are small enough that they fit in less than delta. So I'm going to come and write my second sequence. That's because an approaches a. I know that there exists a capital N. I'll tell you what, let's write it over here. I know that there exists a capital N such that if n is greater than capital N, a of n minus a is less than delta. But now you see it's all coming together. Therefore, if n is greater than capital N, a of n minus a is less than delta, which implies that f of a of n minus L is less than epsilon, because now this a of n right here is taking the place in that sequence. So this first statement, so this implies that comes from this theorem, and then this implies this comes from this assumption. And then so you can see that the f of an must be less than epsilon. So the sequences definitely converge. Okay, now the backwards way is more complicated. So let's see if we can make sense of this. And the way we're going to do it is by contradiction. So what we're going to do is we're going to assume that we have more than one, we're going to assume that every sequence converges to L, but that the limit isn't L. So we're going to assume the limit's not L, and if the limit's not L, then we're going to create a sequence that doesn't converge to L. So the big idea is assume that the limit that of x approaches a of f of x is not L. And then here I'll write a subnote. What we'll do is we'll create a sequence that does not converge to L. So once we have this assumption, then we can go about doing this problem. Well, okay. So if that function does not converge to L, then that means something, and we can go write the negation. Sorry, I'm getting my words wrong. Then we can write the negation of our limit definition to find out what that means. So if that sequence does not converge to L, does not equal L, let's write this so it looks prettier. Does not equal L, then what does that mean? That means that there exists some epsilon value. Let's call it epsilon naught so we know that it's not arbitrary. So there exists an epsilon value such that for every delta value, there exists an x in the set. There exists an x such that 0 is less than x minus a is less than delta, and f of x minus L is greater than or equal to than epsilon naught value. So what that means is, so this is the negation of the theorem as we've seen. Go back to your transitions class. Remember how to negate theorems. And what you see is that there must be some singular epsilon value such that all delta values, no matter which delta value, for every delta value, you can find that point that contradicts it. Okay, so there's no delta value small enough to make this always true. Okay, well now we're going to create our sequence. So the way we're going to create our sequence is like this. So create our sequence as follows. What I'm going to do is I'm just going to let these delta values equal 1 over n. So I'm going to say by let x of n be a value such that x of n is less than delta, x of n minus a is less than delta, maybe I'll say and. Oh, I'll tell you what, let's not use delta there, sorry, is less than 1 over n, and f of x of n minus L is greater than or equal to epsilon naught. Okay, so what you see is that if let x of n be a value such that our x of n's are within 1 over n of a, but the f of x of n's are greater than epsilon naught. And then what you'll see is that two things must be true. First, we see that the x of n values must converge to a, and that's by this statement right here, because x of n minus a is less than 1 over n. But you see that the f of x of n values, they can't converge to L because they're always bigger than epsilon from L. They're never less than epsilon from L. So I didn't quite have the rigor of the book. If you go look at the book, you'll see that it gets a lot more into the details of this proof. But this is at the heart of the proof, and this is the big idea of what's going on. But what's nice about this proof, and what we're really going to enjoy, what I think you all will enjoy as well, is that once we have this proof, we can now make a connection between limits and sequences. And so sometimes it's easier to talk about limits by thinking of the sequences that come their way. And by the way, there's one nice consequence, and let's write that consequence down right now. This means that if you have two sequences, A of n, where f of a of n converges to, a of n converging to a, and the f of a of n's going to one value, let's just call that value L1, and a second sequence, which we'll say b of n, but we want it to converge to that same value, and that sequence converges to a different L2 that are not equal to each other, then what does that have to mean about our limit? Well, if we can find two sequences that go to different limit values, then it must be the case that that limit does not exist, because we can't possibly have those two limit values come together. This is actually at the heart of what you do in Calc 1 when you do the limits from the right and limits from the left. It's that you're taking sequences where all the values are bigger than a, and then sequences where all the values are smaller than a, and those two sequences are coming up with different values. And so since they're getting different values, then the limit can't exist. And so this theorem is a more rich version of that, except we're not even saying from the left and from the right. We're saying any combination of points that leads to A has to always come up with the same limit value. Okay, let's do an example. So we saw this one. I don't know if this was your favorite, but this was the limit as x approaches 0 sine of 1 over x. This graph, you all might remember, looked something like this. This was one of those that we love from back in our calculus days. What happens is the graph comes in, and then as we get closer here, we get, like an infinite number of hills up and down. So what your graph does is, and if you graph this on your calculator, you see something that looks kind of like this. It's going up and down, up and down. Because what you can think it's doing is it's taking a sine graph. And so it's taking a sine graph that looks something, something like this. And it's flipping it backwards. So this hill is, every hill is going to 1 over whatever its answer was. So the hills way out here at infinity are being packed in here at the inside of the graph. Because the 1 over x kind of inverts it. It makes it where the big numbers become small and the small numbers become big. So the hill that's over there by near the number x equals 1,000,000 is now at 1/1,000,000th on this 1 over x graph. And then the hill that's at 1,000,000,000 is at 1/1,000,000,000th at this graph. So all those hills between 1,000,000 and 1,000,000,000 are crammed together really tightly within a really small range here in this graph. Okay, so let's think about this thing. Well, what am I going to do to prove that this doesn't exist? Well, what I'm going to do is use the idea that we just had. That is, I'm going to try to create two sequences that go to different values. And they seem pretty obvious. One sequence is going to be this sequence up here where all the values are 1. And then another sequence is going to be this value here where all the values are -1. So I just have to kind of come and think about what should those numbers be. And once I come up with them, I'll be in really good shape. Let's draw this sign a little prettier so that I can make sense of it. And so my sine graph, let's just start right here. It looks something like this. Let's ask, when are those sine values equal to 1? Well, the sine value that's equal to 1, let's see, that one's pi over 2. That one is pi over 2 plus 2 pi. This one is pi over 2 plus 4 pi. And you'll notice that those values are the values of pi over 2 plus 2 pi times some k value. Maybe I'll say n because that's what we're going to use in just a second. Similarly, if I look for the values where they're equal to -1, that's 3 pi over 2, and then that one is 3 pi over 2 plus 2 pi, and then those values are 3 pi over 2 plus 2 pi times n. And so those values are going to be the ones that show up here at the bottom of all of those. But now what I need to do is I need to do 1 over those to get my value. So here, this is going to be my sequence. So let's come with our sequences. So my first sequence is going to be as follows. My AN sequence is going to be the sequence 1 over pi over 2 plus 2 pi n. And then what you'll notice is that sine of a of n, by the way, these definitely converge to 0 because the n's in the denominator. So these definitely converge to 0. And the sine of a of n is sine of 1 over a of n is sine of 1 over that. So it's sine of pi over 2 plus 2 pi n is always equal to 1. And so that number definitely converges to 1. So you'll see that if I follow the a of n sequences, which are these, I get something that definitely converges to 1. Now let's look at my bn sequences. So I will let bn equal 1 over 3 pi over 2 plus 2 pi n. That again also converges to 0, but now sine of 1 over bn equals sine 1 over gives you 3 pi over 2 plus 2 pi n, and that is now -1, and so that definitely converges to -1. And so what you see, my conclusion is, because those two converge to different values, then my limit has to not exist, right? Since, and I might say since f of a of n converges to 1 and f of b of n values converge to -1, the limit does not exist. because they would have to be converging to the same thing, because if the limit existed, every sequence, no matter what you choose, would go to that same limit value. I don't know about you, I kind of like this. I feel like this is almost a better proof. It's a little easier to deal with, and we're not dealing with all those messy little epsilons anymore. We're not trying to find two values that are more than an epsilon apart. This seems like a nice conclusion. Okay, the last thing for us to think about are limits at infinity, and you all remember doing this, and really all we're doing is we're generalizing those formulas that we came up with in class last time, where we talked about limits at infinity of sequences, but these are now limits at infinity of a function. Let me just write down these definitions. So we'll do the limit as x approaches infinity of f of x equals L. What should that be? Well, if I think of this as a picture, that's a picture where L is here, and we get this asymptote where we have the graph kind of approaching the limit. And if this looks a little bit like a sequence, the answer is that's good. It kind of is like a sequence. And so our definition is going to be really close to the sequence definition. And we'll say for all epsilon greater than 0, there exists, I'm going to use a capital M, such that if x is bigger than capital M, then f of x minus L is less than epsilon. So it's actually almost the exact same picture as what we had, where we have our little epsilon window here, and then we're coming up with a capital M value. And once we get on this side of the capital M value, the sequence always stays close to that window. So the asymptote is behaving just the exact same way as our limit value was when we talked about sequences. So that's really, really similar. The other one's going to feel a little bit different, but it's pretty close. It's pretty close to the definition we came up with in class. And this is the limit as x approaches a of f of x equals infinity. Well, what would that mean? Well, if we think of that as a graph, that's when we have a vertical asymptote, and we have some graph that's looking like this, where it kind of approaches on both sides. And so here, instead of wanting all of our values to be within epsilon of some value, we want all of our values to be infinitely large. So that means for all m greater than 0, there exists a delta greater than 0, such that if 0 is less than x minus a is less than delta, f of x, and I don't want that absolute value sign there, f of x is greater than m. So you see what we've got here. Now we're picking some value m, and we're going to make our little delta window small enough such that all the values in our function are bigger than m, such that all of our values in our function are bigger than m. And this was similar to what we did with the sequences. Okay, once we have limits at infinity, there are lots of things you can prove. Well, if you have two functions whose limit at infinity is L, then what do you think you get if you add them together? Well, you add the L's together. If you get two functions who have a limit that equals infinity and you add them together, you get a limit that's infinity. And so there's lots of interesting questions we can do with these. And you are correct that we will get to do these on the homework and in class. All right, but I have a project for you, and this is really what leads into class next time. So we're going to talk about this in class today, but it's really for the next class period, where we talk about continuous functions. That's the next topic after this. And I want to know, how discontinuous can a function get, right? And if you remember, we kind of know what it means to not be continuous. What it really means is that, you got a hole here, or you got a jump or something. But more importantly, what discontinuous means is that if you take the limit as you approach some value, it is not equal to the value itself. That's what continuous means, because we have this limit value approaching right here, and then we have the actual value. So if I took it and jumped it up here, then I might have my absolute value, my actual value at a different point. So in order for something to not be continuous, either the limit doesn't exist or the value doesn't exist, although for our case, we want the values to always exist, because otherwise it'd be kind of a not interesting problem. So first, can you create a function that has an infinite number of discontinuities? So see if you can do that. Just infinite number of discontinuities anywhere. Okay, then let's up the ante a little bit. can you get a function that has an infinite number of discontinuities on the interval 0 to 1? So that's an infinite number of discontinuities, but within some contained space just between 0 and 1. Finally, can you make it where it's continuous everywhere? Is there a function, are there any functions that are like continuous, or sorry, it should be, oh, these are typos, which is discontinuous or not continuous. And so can you make it discontinuous at every real number? So that is, no matter where you look on the graph, you've got some sort of problem with your limit or your function. And then similar, this is discontinuous. And then can you make a function which is discontinuous at every number except 0? Okay, so this is your task. See if you can do these, see how many of these you do. We're going to talk about these in class. You can look these up on the internet, but please don't, because it'll make class less interesting, and it won't be as valuable. It'll be much more valuable for you to try to imagine your own functions that do these things, and then we'll talk about them next time. So I'm looking forward to this conversation.